Hello, and thank you for joining us for this demo of our text oxidizer. This is a Rust toolkit for natural language processing. And as you may know, Rust is the process of oxidizing iron. So too, this is the process of our toolkit working on NLP in Rust. I am Genevieve Lalonde, and myself and my partner Sawyer Norquist will be presenting our code here. To give you a brief description, we'll be working on Twitter sentiment data sets. And we start out with a basic tokenizer, which is used then in a naive Bayes classifier. And we'll finish it off with doing a bit more precise tokenization using byte pair encoding. So do you want to start off the first demo, Sawyer?
Yeah, so the place I started working is with the basic tokenizer. Basically, simply a set of functions that will take in a variety of inputs and return a vector of tokens representing the tokenized version of that input. The main limitation is simply in the variety of functions available. Given time, I would simply want to be able to support different kinds of input and different kinds of tokenizing, ideally with a simplified interface to use them with. Of a little bit more interest is the naive Bayes classifier. It is a relatively simple two-class classifier designed to predict whether or not a given sentence or string of words falls within a class or not. It has a few limitations. One of the more significant ones is because it relies on the multiplication of very small numbers. We risk running into floating point issues if we try to train or test against particularly large strings of words. So a future improvement could be to involve that. Additionally, it requires handing around the implementer to hand around data structures. So another improvement around that would be to create some internal data state such that you can simply load in your data and operate on it directly with the relevant functions. Over the course of designing and implementing these two crates, I did create a few tests, which as you can see here on screen, currently pass. In addition to help demonstrate their usage, we came up with a basic command line program to drive these modules. Here you can see the first one. I've got a test set up to generate a model. We've got the target class here, the training data, and in this particular case, a set of test data to actually test our model to see how well it performs, which as you can see here, it does a reasonably good job. Then on the backside, we have a predictor. In this case, it takes in a sample file, basically just a list of sentences to compare against the model, which was created in the previous step. Once that is created, it generates another CSV file with the original samples associated with a flag to indicate whether or not that sentence was predicted to be in class on the provided model. Those are the two sections I spent the most time on. Genevieve?
Sorry about that delay there. So I've stolen screen here. So I worked on the byte pair encoding crate primarily, and I'd like to show how that runs here. So you can see here, I'm calling it differently, and I'm able to separate the cargo parameters from the program parameters. And I'm calling the trainer first. This is going to take this CSV file and generate a vocabulary from it. And that vocabulary will be of size 200 tokens specifically. And it was able to finish there pretty nice and quick. So let's go ahead and take a look at that file. So this is the vocabulary, and you can see at the start of the vocabulary, we just operate on the letters. And after we've developed the vocab, these are some of the letters that are still composing some of the less frequent words. Now, if we check out the tail end of that vocabulary, you can see the tokens that were generated later. And these are longer words. In fact, this token right here is one I artificially added, which indicates the end of a word. So this is the complete word king. And this here would be the 200th token. Now, in addition to training the model there, we can also tokenize with it. So let's go ahead and run that. This is the PPE tokenizer, and it's taking the text that is in this CSV and a vocabulary. This is one that I generated earlier, which is a little bit larger, and it is using that to tokenize. Now, as far as limitations and future work, I've got a couple of areas. One is the vocab size limit. It's currently limited to 255 characters because of the data type that I chose. So I would definitely like to convert that, but it's being handled later in the programming. So it's not just a simple case of changing that. And then additionally, I'd like to change how I'm selecting those two tokens that are going to be merged. I'd like to make it more object oriented. Here you can see I'm passing in a corpus, at least it is a reference, but it's the whole corpus. And I'm building that entire set of candidates every single time, whereas it could just be updated. So I definitely like to improve those in the future, get some better performance. And with that, I'd like to sign off. I'd like to thank Professor Bart Massey here, and I think I speak for us both when I say that we have learned so much, not only about Rust and had a lot of fun with it, but also about natural language processing. So that's been really cool. And I just want to say thanks for turning us into Rustaceans.
Thank you.